What if I told you there could be an infinite number of copies of you reading this exact same sentence right now? According to theoretical physics, infinite space creates endless possibilities, like a cosmic hall of mirrors stretching beyond imagination. In the next few minutes, we'll journey past the boundaries of our observable universe, exploring what might exist in those unreachable regions. From fascinating cosmic patterns that potentially repeat themselves to the mind-bending mathematics, suggesting that somewhere, beyond what our most powerful telescopes can detect, entire worlds might exist that mirror our own in ways both familiar and surprising. The edge that isn't. Have you ever wondered where the universe ends? When we look up at the night sky, it seems to extend endlessly in all directions. But does it actually have an edge? A place where everything just stops? The truth is more surprising than you might think. Our observable universe has a boundary located approximately 46.5 billion light years away from Earth in any direction. That's a staggering distance, about 273 sextillion miles. But here's the key point. This boundary isn't an actual edge. It's more like a horizon of visibility. Think about standing on a beach and looking out at the ocean. You can only see so far before the curvature of the Earth prevents you from seeing any further. Ships sail beyond what you can observe, not off an edge. The cosmic horizon works similarly. We're limited by the fundamental speed limit of the universe, light. This cosmic horizon exists because light from beyond this distance hasn't had time to reach us since the beginning of the universe. Light travels incredibly fast, about 186,000 miles per second, but even at that speed, it can only travel a finite distance in a finite amount of time. The universe has existed for approximately 13.8 billion years, which means that light has only had 13.8 billion years to travel toward us. You might wonder why our observable limit is 46.5 billion light years rather than 13.8 billion light years. This discrepancy comes from cosmic expansion. The universe has been expanding since the Big Bang, stretching space itself. Imagine you send a letter to a friend who lives 10 miles away. While your letter is in transit, the distance between you somehow stretches to 30 miles. The letter still arrives, but now your friend is much farther away. Something similar happens with light in our expanding universe. The light from distant objects began its journey toward us shortly after the Big Bang, when those objects were much closer. During the billions of years it took for that light to reach Earth, the universe expanded dramatically, carrying those objects much farther away. What's critical to understand is that this horizon isn't a physical boundary, just the limit of what we can observe. There's no wall, no fence, no sudden change in the fabric of space. There's simply a distance beyond which light hasn't had time to reach us yet. The universe almost certainly continues beyond this horizon, but we have no way to directly observe what's out there. This is a challenging concept because it contradicts our everyday experience. In our daily lives, boundaries are typically physical things. Walls, fences, coastlines. But the boundary of our observable universe is a limitation of perception. Like being in a dark room with a flashlight, the edge of your light beam isn't the edge of the room. It's just the limit of what you can see. What defines the edge of our observable universe is simply the distance light has been able to travel to reach us since the beginning of time. And because the universe is 13.8 billion years old, no information from beyond our cosmic horizon could possibly have reached us yet. This distinction between an edge and a horizon is crucial for understanding everything else we'll explore about what might exist beyond. If there's no actual edge to the universe, just a limit to what we can see, then what lies beyond? Does space simply continue forever? Are there other regions of space similar to ours? Could there even be other universes entirely? The concept of our cosmic horizon reveals something profound about how we understand the universe. Our knowledge is fundamentally constrained by the physics of observation. We can only know about things that can, in some way, send information to us. And since information in our universe cannot travel faster than light, there will always be parts of reality that remain unobservable to us. Astronomers and physicists have developed various ways to study the observable universe in remarkable detail. We've mapped the cosmic microwave background radiation, the afterglow of the Big Bang. We've cataloged billions of galaxies. We've detected gravitational waves from merging black holes. But no matter how powerful our telescopes become, they cannot see beyond the cosmic horizon. Despite this limitation, scientists have developed theories about what might exist beyond our observable limit. Using mathematics, physics, and logical inference, researchers have proposed several possibilities for what the larger cosmos might look like. These theories are based on our current understanding of physics and cosmology, extended to regions we cannot directly observe. Our cosmic horizon isn't static. As time passes, light from slightly more distant regions reaches us, gradually expanding our observable universe. But because the universe's expansion is accelerating due to dark energy, there are regions of space that will forever remain beyond our horizon. The light from these regions will never reach us, no matter how long we wait, because space is expanding faster than light can travel through it. This accelerating expansion creates a fascinating situation. Our cosmic horizon has both a past limit and a future limit. The past limit is the distance beyond which light hasn't had time to reach us yet. The future limit comes from cosmic acceleration regions of space, receding from us so rapidly that their light will never reach us, even given infinite time. This distinction between edge and horizon fundamentally changes how we think about our place in the cosmos. Understanding that we're limited by a horizon of visibility rather than a physical boundary opens up entirely different possibilities, which we'll explore in the following sections. Infinite space, the first theory. Now imagine the universe doesn't end at our cosmic horizon. What if space simply continues forever with no edge at all? This is our first and perhaps most straightforward theory about what exists beyond our observable universe, and it's one that most cosmologists today find compelling. The idea is remarkably simple. Space extends infinitely in all directions. No matter how far you travel, you'll never reach an end or boundary. This concept aligns with our best observations. The data from satellites like WMAP and Planck, which have measured the cosmic microwave background radiation with incredible precision, indicate that the universe is flat to a very small margin of error. In cosmology, a flat universe is compatible with infinite space extending endlessly. When astronomers look at the largest structures in our universe, the distribution of galaxies, galaxy clusters, and cosmic voids, they find a striking pattern. On sufficiently large scales, the universe appears remarkably uniform, with matter distributed evenly in all directions. This uniformity suggests the universe continues infinitely with the same properties throughout. But if there is no edge, the landscape of space must have infinite repetition. In an infinite universe where space extends forever, patterns must eventually repeat themselves. This is a logical necessity based on quantum physics. The reason is that there's only a finite number of ways particles can arrange themselves in any given volume of space. Quantum physics tells us that particles can only exist in certain states. The possibilities for particle arrangements are astronomically large but limited. It's similar to a deck of cards. There are only so many ways to arrange 52 cards. Shuffle them enough times, and eventually the same sequence must appear again. If you have a finite number of possible arrangements but infinite space to work with, mathematics dictates that eventually all possible arrangements will appear, and they'll appear an infinite number of times. This mathematical certainty leads to a staggering conclusion. Given enough distance, an unfathomably large distance, but still a finite one, every possible arrangement of matter must repeat, including the exact arrangement of particles that make up Earth, our solar system, and even you. The concept builds on what physicists call the cosmological principle, the idea that on large scales, the universe looks essentially the same everywhere. There are no special locations or directions in space. This principle, supported by our observations, suggests that the laws of physics work the same way everywhere. If space is infinite, those same laws would produce every possible outcome given enough volume. Consider the implications. Somewhere beyond our cosmic horizon, there would be another solar system identical to ours, orbiting an identical star with an identical Earth. These wouldn't be similar copies. They would be absolutely identical down to the subatomic level. In an infinite universe, there would be infinite copies of Earth. Some would be exactly identical to ours in every detail. Others would differ in tiny ways. Perhaps on one of these alternate Earths, you chose a different breakfast this morning. Every possible variation of our world would exist somewhere. The distance to find an exact duplicate of our observable universe is almost incomprehensibly large. Physicist Max Tegmark has calculated that the nearest identical copy of our observable universe would be approximately 10 carat 10 carat 1 18 meters away. That's a 1 followed by 10 to the power of 118 zeros, a number that defies meaningful comparison. For context, the observable universe is approximately 8.8 times 10 to the power of 26 meters across, which suddenly seems tiny by comparison. Even finding a region where just our galaxy is duplicated would require traversing distances far beyond anything we could ever observe. What's fascinating about this theory is that it requires no exotic physics or speculative assumptions. It simply takes quantum physics and extends it to the logical conclusion of infinite space. If space continues forever and the laws of physics remain constant, these duplicate regions must exist. This means that somewhere beyond our cosmic horizon, another version of you is reading this exact same sentence. Every possible decision you could make is being made by some version of you in this infinite expanse of space. These cosmic duplicates aren't alternate timelines or parallel dimensions. They exist in the same space as we do, just at unfathomably large distances beyond our cosmic horizon. They're as real as we are, subject to the same laws of physics, but forever outside our ability to observe or contact. Some physicists find this implication troubling. The idea that everything in our lives is being duplicated infinitely throughout space seems to diminish our uniqueness. But others see it as a fascinating consequence of the mathematics that governs our universe. Think about it like shuffling an infinite number of finite card decks. Eventually, you'll create every possible sequence, and you'll create each sequence an infinite number of times. The same principle applies to the arrangement of particles in space. Each copy exists independently, unaware of the others. You'll never meet your cosmic duplicate, and neither of you can influence the other. The speed of light ensures these regions remain forever causally disconnected. The theory of infinite space with repeating patterns represents the simplest explanation for what might exist beyond our cosmic horizon. It doesn't require new physics or extra dimensions. It simply extrapolates what we observe in our region of space and extends it indefinitely. What's remarkable is that this mind-bending conclusion that infinite copies of you exist stems from straightforward physics and mathematics. It's a logical consequence of infinite space combined with quantum physics' finite possible states. How far to your cosmic twin? If there are copies of you in an infinite universe, how far away would the nearest one be? It's a question that moves from philosophical curiosity to mathematical calculation, and the answer is truly staggering. Mathematician and physicist Max Tegmark has tackled this problem directly. He calculated the actual distance you would need to travel to find an identical copy of our observable universe. His result, the nearest identical copy would be approximately 10 carat 1 18 meters away, a distance so vast that if you tried to write this number, you'd need more zeros than there are atoms in the observable universe, estimated at 10 to the power of 80. To grasp this scale, imagine counting every grain of sand on every beach on Earth, then replacing each grain with an entire observable universe. The distance to your cosmic twin would still vastly exceed this combined scale. Our entire observable universe, approximately 93 billion light years across 8.8 times 10 to the power of 26 meters, would appear smaller than a subatomic particle in comparison. This enormous distance results from quantum physics and the number of possible configurations particles can take in our observable universe. The observable universe contains approximately 10 to the power of 118 quantum fields, each existing in different states. When calculating all possible arrangements of these quantum fields, you get an astronomical number that determines how far apart identical regions must be in an infinite universe. The mathematics relates to the quantum state of the universe. In quantum mechanics, particles exist in superpositions of many possible states until measured. The total number of possible quantum states for our observable universe is finite but incredibly large. An identical copy means a region where every quantum field exists in exactly the same state as in our observable universe. Every particle, wave function, and quantum fluctuation perfectly matched. Tegmark's calculation doesn't require speculative physics. It's based on standard quantum mechanics and the assumption of infinite space. If space extends forever, and quantum physics limits the possible states, these duplicates must exist as a mathematical certainty. Interestingly, partial copies would be much closer than complete duplicates. Tegmark calculated a hierarchy of distances. Regions duplicating just Earth would be about 10 carat 29 meters away, still an enormous distance beyond our cosmic horizon, but much closer than duplicates of the entire observable universe. Following this pattern, the larger the region you want to duplicate, the farther you must travel to find an identical copy. This resembles matching coin flips. Matching 10 flips happens frequently, matching 100 is rare, and matching 1,000,000 would require flipping coins longer than the age of the universe. Similarly, finding a perfect copy of just you requires traveling approximately 10 to 29 meters, still beyond our observable universe, but closer than finding an identical copy of everything we can see. Quantum uncertainty adds another dimension to these calculations. Quantum mechanics imposes a fundamental limit on how precisely we can know a system state. While perfect duplicates might not be theoretically possible at the finest scales, duplicates identical in all measurable macroscopic ways would exist at the calculated distances. Our observable universe extends about 46.5 billion light years in any direction, 4.4 times 10 to the power of 26 meters. Compared to the distance to our cosmic twins, our observable universe is like a single atom in an ocean. Even traveling at light speed for the entire future history of our universe would cover only an infinitesimal fraction of the distance to our nearest duplicate. This vast separation explains why we've never detected these theoretical duplicates. They lie far beyond what we could ever observe. Even with impossibly powerful telescopes, we would never see these cosmic twins. Light from these regions hasn't had time to reach us since the Big Bang, and due to the accelerating expansion of the universe, it never will. Some find this conclusion unsettling as it seems to challenge our sense of individuality. Others find it comforting. In some sense, nothing is truly lost in an infinite cosmos where every possible variation of our lives plays out somewhere. Every road not taken, every decision made differently exists, separated by incomprehensible distances. The concept of cosmic duplicates raises philosophical questions about identity. If an identical copy of you exists with the same memories, thoughts, and physical structure, is that person also you? Or a distinct individual who happens to be identical? These questions extend beyond physics into philosophy of mind and personal identity. For now, these cosmic duplicates remain theoretical, a logical consequence of our understanding of physics and cosmology. We can calculate their distance, but we'll never observe them directly. They exist beyond our cosmic horizon in regions forever invisible to us. Yet mathematics suggests they're out there, living lives identical to ours across distances that exceed our ability to truly comprehend. Dark flow, evidence of something beyond. Could we already have evidence of massive structures existing beyond our cosmic horizon? Some scientists believe we do, and it comes from an unexpected discovery about the movement of galaxy clusters throughout our universe. In 2008, a team of astronomers led by Alexander Keshlinsky made a discovery that sent ripples through the scientific community. Using data from NASA's Wilkinson Microwave Anisotropy Probe, WMAP, satellite, they were studying the cosmic microwave background radiation, the ancient light left over from the Big Bang that permeates all of space. By examining how galaxy clusters interact with this radiation, they uncovered something remarkable. Galaxy clusters across a large region of the observable universe appeared to be moving in the same direction at speeds between 600 and 1,000 kilometers per second, about 2.2 to 3.6 million miles per hour, extraordinarily fast even by cosmic standards. More importantly, these clusters weren't moving randomly as expected. They were streaming collectively toward a specific point in space between the constellations of Centaurus and Hydra. The researchers named this phenomenon dark flow, presenting a significant challenge to standard cosmological models. According to our understanding of the universe, on very large scales, matter should be distributed fairly evenly, and the movements of galaxy clusters should be essentially random. There shouldn't be a preferred direction for movement across such vast distances. The most fascinating aspect was what this might imply. When scientists looked toward this region of apparent gravitational influence, they found nothing visible that could account for such a powerful pull. There simply wasn't enough observable mass to explain why so many massive galaxy clusters would be moving toward it. This led to an extraordinary hypothesis. Perhaps these galaxy clusters are being pulled by something massive that lies beyond our cosmic horizon, something we fundamentally cannot see because light from that region hasn't had time to reach us since the Big Bang. Dark flow could be evidence of structures existing outside our observable universe. Perhaps even another universe entirely that existed before the inflationary period of our universe, or a massive concentration of matter that formed before inflation. The technical measurement behind this discovery involves the kinematic Sunyaev-Eldovich effect, KSZ. This effect describes how cosmic microwave background radiation is slightly altered when passing through hot gas in galaxy clusters. As radiation passes through these clusters, it interacts with high-energy electrons, causing slight changes in temperature. By measuring these minute temperature differences, scientists can determine how the clusters are moving relative to the cosmic microwave background. These temperature patterns across the sky revealed the coherent motion of clusters, suggesting an unseen gravitational influence pulling on the very fabric of our observable universe. If confirmed, dark flow's implications would be profound. It would mean that our cosmic horizon isn't merely a limit to what we can see, but a boundary beyond which lie structures massive enough to influence our observable universe's dynamics. This hidden gravitational influence could be shaping the destiny of our galaxy and countless others, pulling us towards something we may never directly observe. However, dark flow has become the subject of significant scientific debate.